Greetings to all. So in this video we are going to discuss about system design consideration, point to point link design. So this is under unit 5, optical communication systems and networks. Unit 5. So we can just split this unit 5 into three parts. First part deals with system design consideration, point to point link design, link power budget, rise time budget. Second part we can call it as WDM, wavelength division multiplexing, passive, DWDM components, elements of optical networks, SONET SDH, optical interfaces, SONET SDH rings and networks. Third part, high-speed light wave links, OADM configuration, optical Ethernet and solid term. So in this video, we are going to discuss system design consideration for point-to-point link design. So next, we can just say and how to select. That is, what is the selection of optical. So what will be the optical source? So that depends upon the emission wavelength. That emission wavelength depends upon the acceptable attenuation as well as dispersion. Next one is spectral line width, and that is depends upon the acceptable dispersion. So say for example, for LED it will be wide, and for laser which will be narrow. The spectral line width of the LED is wide. At the same time for the laser it will be narrow. Next parameter that has to be considered while selecting the optical sources, optical power into the fiber. So what is the output optical power from the optical source to the fiber? For example, suppose if you are going to use that optical source as an LED, then that output power from the LED is low when compared to the laser. Next is nothing but stability, reliability as well as cost. So these are all the factors that has to be considered while selecting the optical source. Next is nothing but selecting the detector. So as I told you, first you have to consider, that is first you have to look into that what is the type of the detector that has to be used. Again here also it is depends upon the application. Suppose if it is an avalanche photodiode which has the high sensitivity, but at the same time the circuit is very complex. And it has a high bias voltage in the range of 40 volt or sometimes more than 40 volt. And it's very expensive when compared to the pin photodiode. In pin photo, suppose if you are going to select a pin photodiode, which will be simpler and thermally stable, which will have the low bias voltage in the range of 5 volt or less, and it's less expensive. So obviously based upon the application, either we can just select avalanche photodiode or pin photodiode as a detector. And what are the parameters that are responsible for the performance of detector? Responsivity. So what is the responsivity is, which is depends upon the gain as well as quantum efficiency. The next one is operating wavelength and spectral selectivity. Next is speed in photosensitive area. Last one is sensitivity, which is obviously depends on noise and gain. And what is the typical bit rate at different wavelength? So this is a wavelength range 800 to 900 nanometer. So typically we can say it is in multimode fibers. 1300 nanometers lowest dispersion, 1550 nanometer lowest attenuation. So as we know that we will have the three attenuation windows based upon the wavelength. One is 800 to 900, second one is 1300 nanometer, third one is 1550 nanometer. So suppose if you are going to use the optical sources in LED, then which will give you the that is a bit rate of 150 megabits per second kilometer. Laser which will give you 2500 megabits per second. And similarly for that 1300 nanometer wavelength, we will have the 1500 megabits per second kilometer. Here in case of laser, 25 gigabits per second kilometer. And in case of laser, and if it is made up of indium gallium arsenide phosphorus laser. And suppose at wavelength 1550 nanometer, we will have the bit rate of 1200 megabits per second kilometer. And here for the laser system, we will have up to 500 gigabits per second kilometer. So this is the best suitable for the maximum radiation. The next comes design consideration. So while designing this optical transmitter or optical receiver, it is very necessary to consider there are two factors and which can be considered for the design consideration of optical link. One is link power budget, next one is rise time budget. That is, here there is an enough power margin in the system to meet the given bit array. Rise time budget is nothing but each element of the link is fast enough to meet the given bit rate. So based upon this one, we can able to find out what is the link power budget and what is the rise time budget. Based upon this one, we can able to come to the conclusion that what should be the considerations. So these two budgets give necessary conditions for the satisfactory optical link power or loss model. So as we discussed in that first slide, that is block diagram of point to point link, here it is replaced by the components. So first of all, here there is a transmitter which will have the optical source as I told you, and that optical source that will be connected at one end of the optical fiber by means of connector, and there will be splices. And here at the other end again there will be connectors as well as splices, and finally that will be connected to the optical receiver, and that optical receiver again which will consist of detectors. Now this is the formula that has to be followed to find out the total power loss. So total power loss which is equal to PS minus PR, where PS is nothing but source power and PR is nothing but receiver sensitivity, which is also is equal to MLC, which is nothing but M is nothing but number of connectors used in the link, and LC is nothing but it's a connector loss, plus small n is nothing but number of splices connected in this link, and LSP is nothing but that is a splicing losses, and plus alpha F into L, where alpha F is nothing but fiber attenuation constant or fiber attenuation coefficient, and L is nothing but length of the fiber. So length of the fiber is nothing but the distance between these two. That is distance between transmitter and receiver. We can call it as length of the fiber. And finally, system margin. So this is the formula. So by using this formula, we can able to find out what is the total loss expected for this particular link. So power budget example. Say for example, I'm considering this kind of, it is one problematic question. Specify a 20 megabits per second data rate and bit error rate of 10 power minus 9. With a silicon pin photodiode at 850 nanometer, the required receiver input signal is minus 42 dBm. Select gallium aluminum arsenide LED that couples 50 milliwatt into a 50 micrometer core diameter fiber flyhead. Assume a 1 decibel loss occurs at each cable interface and 6 decibel system margin. So this is the consideration. Here the question is that, so the question is we have to find what is the possible transmission distance between transmitter and receiver. So possible transmission distance is nothing but the distance between transmitter and receiver. So that is the question. So here we can just use this formula what we discussed in the last slide. The total power loss, we know that formula that PS minus PR, which is also is equal to 2LC. Since here we are not using that what is that number of splices there, so that we can just use that formula 2LC plus alpha L plus system margin. So this consideration, that is this problematic question, we can just represent in terms of graphical representation also. So this is the actual graphical representation for the given statement. So here there will be an 6 decibel system margin as it is given in the problematic question, and assume there is an 1 decibel loss occurs at each cable interface. So that is mentioned here. Here it is in connector loss. So here it is in, this is also connector loss, which is around 1 decibel loss for each connection. And here it is in, here there is an system margin. And next one is nothing but, here it is 20, that is here it is 13 decibels. And here it is 42. Here it is receiver input signal is minus 42 dBm. So here it is approximately 42 dBm. It is power level. Y-axis represents power level and x-axis represents distance. So here what you are going to do is we are going to find out this distance. So they given the remaining thing and all, that is 3.5 decibel per kilometer for every cable interface. Here it is given here 3.5. Okay. So from this we can able to find out what is the that possible transmission distance. Okay, so by using this formula we can able to find out, and here it is 42 dB, that is required receiver input We know that PS is nothing but it is an that is a source power. We can just write it as, and here it is minus 42 dBm, that is 42 dBm. And receiver sensitivity, here receiver sensitivity is here, so it is around 13. So you can just substitute this 13 dB here, that is equal to 2 into LC is nothing but here it is connector loss. Here connector loss is given as 1 decibel, that is 1 decibel loss occurs at each cable interface, so that we can just substitute it as 1 decibel here, and alpha into L plus, and system margin is nothing but it is given as 6 dB. So we can just substitute 6 dB here. Now 42 minus 13, which is nothing but 29 dB, which is equal to here 6 dB plus 1 dB, 6 dB plus 2 dB. We can call it, we can just write it as 8 dB into alpha into L. So 29 minus 8, which becomes 21, which is equal to alpha into L. So here the question is, we are going to find the possible transmission distance, so that we can just give this L in the left hand side, the remaining to the right hand side. So 21 dB by alpha. So here alpha is given as 3.5 decibel per kilometer cable loss. So we can consider this 21 decibel by 3.5 decibel per kilometer, so that the L capital L is equal to 6 kilometer. So this link power budget, as I told you, which is represented in graphically. Now, including this 6 decibel system margin, the possible transmission distance for a cable with a fiber attenuation of 3.5 dB per kilometer, then 6 kilometer transmission path is possible. So that is the conclusion from this. So what's the conclusion is, for the given statement, and we can able to find out what is the possible transmission distance between transmitter and receiver by using this formula. The same thing that is represented graphically. So this is power budget example. And this is another example for the power budget. Again, it is given, the statement is given. So according to the statement given, we can just list out that statement in terms of spreadsheet for calculating the optical link power budget. So this is according to the statement given. Laser output is 3 dBm. Here it is, laser output is 3 dBm. APD sensitivity at 2.5 gigabits per second is equal to minus 32 dBm. Allowed loss, it is 3 of 3 minus of minus 32. So this is the allowed loss. Source connector losses 1 decibel. Source connector loss, which is given as 1 decibel. And jumper plus connector losses 3 plus 1 decibel. Cable attenuation for 60 kilometer distance is 18 decibel. And jumper plus connector losses 3 plus 1 decibel again. Receiver connector losses 1 decibel. So this is according to the statement given here. Here it is 1 decibel connector loss is given, that is given here. And 2 at each end because of the jumper cables. So this fiber joint which is connected by means of 2 jumper cables, so that we can just writing this jumper and connector loss 2 times. 3 plus 1 dB, 3 plus 1 dB. Now from this we are going to find out what is the power margin in terms of decibels. So here it is 3, and here it is minus 32, but here this allowed losses, this 3 minus of minus 32, so that 3 plus 32, it's nothing but 35. So the power margin is 35 decibels. 35 decibels. Here the connector loss, since it is in loss, so that we can just minus 35 minus 1 decibel, we can write it as 34. And then 34 minus 4 decibels, 30. 30 minus 18, 12. 12 minus 4 decibels, 8. 8 minus 1 decibel, 7. So this is the final margin according to the optical link power budget. So like this we can able to find out the final power margin for the given statement. So according to this given statement, so our final answer is, the final margin is 7 decibels. So likewise we can able to find out the power budgets. So next one is rise time budget. So the rise time budget analysis which determines the dispersion limitation of an optical fiber link. So here this total rise time, and that can be calculated by using this formula. So where this TTX is nothing but transmitter rise time, and T mod is nothing but here it is modal dispersion rise time. GVD is nothing but group velocity dispersion rise time, and TRX is nothing but receiver rise time. Okay, so whole root of T, T, TTX square plus T mod square plus T GVD square plus T RX square whole root. So by substituting the given value according to this statement, we can able to find out the what is the rise time of the system given. So here we'll be using two constants here. So this V naught and V and which are given in terms of megahertz. So that we can say that always this time period that is this rise time always will be in nanoseconds. So this is an example for rise time budget. So this is the given statement. So according to this given statement, from this we can able to write what is that transmission, that is the transmitter rise time, and what is the dispersion rise time, what is the modal dispersion rise time, and what is the receiver rise time. So by substituting all these rise times given according to the statement, we can able to find out the overall system rise time, and which is obtained as 30 nanoseconds. So this value which falls below the maximum allowable 35 nanoseconds. Here allowable value is given in terms of 35 nanosecond rise time. So there is a degradation for our 20 megabits per second non-return to zero data stream. So therefore zero point 0.7 per bit rate. So the choice of components was thus adequate to meet our system design criteria. So likewise, we can able to find out whether the system that is a requirement is the given requirement is that is adequate or not. So that is the actual purpose of both link power budget and rise time budget. Thank you for your patient listening.